if we have, so basically the thing is we're looking at something like a function which is equal to u plus iv. This is the typical notation. So this, both u and these u and v, both functions of a real variable. So this would be a complex valued function of a real variable. Right? So terminology much like the same. The real part of f is what? Is u, right? The imaginary part of f, v, in my current setup. All right? Let's see here. So, for example, let me keep this definite. I'm gonna do an uber definition if you don't mind. Throw a bunch of stuff in here. If we calculate df dt, guess what we do? We do du dt plus I dv dt. I taught calculus 3 this morning at 8:15, and we were studying the calculus of space curves, calculus of paths. This is exactly that definition. We differentiate a vector valued function component-wise, right? Complex numbers, just two-dimensional vector. This is exactly that calculus. And then also, integral of f dt would be the integral of u dt plus I times the integral of v dt. Now, we need the integral less in here, but for the sake of completeness. And also because I've got a really cool example to show you. Now, an example, let's see, what example am I on? 5? Example 5. So if we look at f of t equal to e to the it, well, okay, what's that? That's cosine t plus I times the sine of t. Okay. So what's the real part of f? Yeah, cosine t. What's the imaginary part of f? Sine t, yeah. Very good. Okay. What if I have, example 6. Here's another one. Let's say g of t equals t to the a plus ib. What should this mean? I'm going to tell you what it means. So in other words, I'm saying t to a complex power. That's weird, right? A little bit weird. But here's how it goes. That's actually t to the a, t to the ib. But then we got to make sense of what should t to the ib mean. Let me show you how we do that. So what I'm showing you right now is basically just a heuristic, all right? What I'm going to come to at the end of all this is just the definition of this function, okay? But so t to the ib you could look at as the, let's see here, how does it go? I'm just, I guess it's the exponential of the log of IB, right? That seems like it should be reasonable. And then curses. No, it's not right. I've messed this up. I think I got to go the other way around. It's the log of the exponential. Oh, stink. Oh yeah, maybe. I'm sorry, guys. I just all of a sudden have a just giant gaping hole in my memory here. So that should be what? That would be times log e. Well, that gets us right back where we started.
Well, they're equal.
That's oh. All right. I'm having trouble remembering curses. I think t to the. Let me change this. I know it is entirely ridiculous that I'm doing this, but you'll forgive me. I just know that I usually use x in this part of the course. It might help jog my memory. Don't tell any math professor I did this. Okay, so what should x to the IB be? I believe x to the IB was the cosine of the natural log of b times the natural log of x plus I times the sine of b times the natural log of x. I'm assuming x is positive here. Well, would that make sense? This would be e to the what? This would be e to the I b log x, right? Which, if there's any justice, should be e to the what? E to the log x to the IB. Yeah, there we go.
That doesn't work with t, right?
It would have worked with t too. It's just it wasn't working for me today. Okay, anyway, long story short. So what I'm getting to here, guys, is that g of x is equal to x to the a cosine of b log x plus I x to the a sine of b log x. So what's the real part of g? Let me just underline it if you don't mind. I'm tired of writing all this. This guy, real part. Right? This part over here, the imaginary part. These are actually pretty much the main two examples I need for this course in terms of fun new things that are complex valued functions of a real variable. Now, calculus. All right, hold your plasmine. Just hold your breath. It's very exciting what's about to happen here. So theorem d dt of e to the lambda it is equal to lambda e to the lambda it. Oh, I'm sorry. I don't want the I there. E to the lambda t is just lambda e to the lambda t. And d dt of x to the c power is c x to the c minus 1, right? But I should emphasize here, lambda could be alpha plus I beta, and this c could be a plus ib. I mean, I'm talking about complex arguments there. And yet still the usual calculus works. We have no right to expect that, and yet it's true. Yeah.
We treat the I as a number as opposed to a variable.
Yes, I is a number. It is.
Right.
Yeah, that is true. It is a square root of minus 1, if you like. Now the proof that these are true involves a lot. I can do one or the other. I can't do both. Which one do you want me to prove?
Bottom one.
Bottom one, okay. So that's, as we've just defined here, x to the a cosine of b log x plus I x to the a sine of b log x. All right. Oops. Yeah, you guys do that. I'll take points off. So just so you know, like it annoys me when people randomly give me answers that are some admixture of x and t in here. Like, I used to look the other way on it, but I've grown older and crankier. And so, like, if I see t and x in a solution that should just be t or just be x, I will take off something. Because I feel like it's a little bit important. I mean, I know test time pressure, blah, 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 blah. But anyway, so I'm just saying it's hypocritical of me not to complain about me doing it, since I'm going to complain about you doing it. All right, so this is ax to the a minus 1. A is a real number, right? Nothing new there. Cosine b log x. And then minus x to the a sine of b log x. Oh, goodness gracious. And then times b over x, right? It's not that bad, actually. I retract my, let's see here. And then plus I a x to the a minus 1 sine of b log x. I like teaching this time of day. This is the time of day I don't care. Let's see here. Plus I x to the a cosine log b. Oh, b log x.
It's about the time of day you're usually grading tests, too.
No. Wait till I'm angry at my children, then I grade them. Let's see here. No, I don't know. I think I already differentiated, so I shouldn't have ddx out here. Grief. Idiot. All right. Me, not you. Is that it? I mean, two product rules, right? And I'm using the definition of the derivative. I differentiate each component separately. Now we just have to put it back together, right? So this is a plus ib. Let's see here. X to the a minus 1. See, this is a minus 1 as well. And this minus is an I squared. And that's why we have, son of a gun. Where's this term coming from? It's coming from this guy and this one. Yeah. And then I think we have plus I times a plus ib, x to the a minus 1 sine of b log x. If I look at this right, let me see there. So let's see. IA x to the a minus 1 sine. That is exactly this one, right? That's what's giving me this a here, right? See that? How about the other one? I hope it's the remaining term, otherwise we're in trouble. So I times I, see this? That's a I squared in disguise, right? And then x to the a divided by x is x to the a minus 1, agree? And so, this is, factor out the a plus ib, x to the a minus 1 cosine b log x plus I sine b log x, which is exactly a plus ib times x to the a plus ib minus 1, aka c x to the c minus 1. You see what I'm saying? We have no right to expect this works. It's special and wonderful that it works. Right? And yet it does. Similar, like this involves an interplay between like the product rule, the adding angles, formulas for sine and cosine. It's got all kinds of stuff in it. It's really about the same length. Yeah. Oh, it's time? Sorry, thanks. What time is it? Oh, it's go time. All right, go away. Why are you still